This is video help for problem 15.10 in the old, and it's really 15.9 in the new. In the old, ignore part C. We should be talking about gray matter swelling into adjacent voxels instead of a change in density there. So ignore part C. As you'll see, actually, if anybody and everybody just pays attention to 15.9 as written in the new edition, we'll be in good shape. By the way, Mingdong told me that sometimes when I'm recording this, I'll go in and out of focus because I move my hand up and down, as you can see that happens. So I'm going to try to keep my hands, sort of close to the paper and just try to avoid having them raise up because I don't know how to freeze the focus. Anyway, problem 15.9, part A. We imagine it's a spin echo experiment so that instead of T2 star, we're dealing with T2 weighting all the time. Or, as we know, we'll see in problem 15, the next problem, 15.11, we just assume there are no T2 star effects. Back to here. Usually we've got just one tissue, one T1 and one T2 for a given voxel. But if we have them mixed together, we need to average them. And we need to average them through R, the rate at which the transition, the relaxation or the decay occurs. That's the fundamental thing, the rate. Well, what we have to do here is ask how many of the protons, really we're always talking about hydrogen protons. How many of the hydrogen protons come from the water? How many of them come from the gray matter or whatever the gray matter here. And so we're averaging over the protons and the hydrogens. So we're counting up them. But of course, when we're averaging, we got to have a fraction, a percentage. So I take the density of the protons from water times the volume of the water, and then I normalize it. And it's really, the answer you get is almost the same as if you just ignore the density differences and just pay attention to the volume difference. And so when you go through that, you're going to find out that the percentage changes in T1 and T2 are not very different. In fact, they're just a 1 or 2% difference. So in part B, the bigger that delta T is, we're supposedly then, if it changes a lot, then the T2 weighting would be, if it was T2, if the change in T2 was much bigger than the change in T1, then T2 weighting would be the way to go. But they're so close. If you take strict differences, then T2, well, you can look at it. Finally, in part C, you're just taking the optimal TE for T2 weighting, the optimal echo time. It's same equation number in both editions. And by the way, T2 star is replaced by T2 again. We're ignoring the delta B effects. Now, or you did a spin echo. Now here in this part, we're just comparing two different adjacent tissues, two adjacent voxels. And if you put their densities equal, you're going to calculate TE optimal, and you'll see that it's just the average of the T2s. Well, if you actually consider the density differences and calculate it then, you're going to get it rather less. And that's because the delta, if we defined a delta here, T2b equals T2a times 1 plus delta, as in the problem here, the delta is 20%. It's not that small.